Hey everybody, welcome back. This is College of the Sequoias. We're going to do college algebra. This is chapter 11 we're looking at. It's sequences and series. And I hope this goes well because I'm filming this early in the morning. I want to make sure it's up so you have it for a week. Here we go. So sequences and series, let's just start off with a definition. A sequence is a list of numbers that follows a pattern. Follow some sort of pattern. Okay. And I'll give you an example in a second, but I want to give another one. If we call it a finite sequence, a finite sequence has a set of natural numbers. Natural, that doesn't look good. Let's try it again. Natural numbers of the form we have 1, 2, 3, 4, ... n. Now these ... dots, when we have ... like that, these are ellipses. And when you see these in between two numbers in a numerical sequence, the ellipses mean keep following the pattern. Until you reach the number following the ellipses. Following that. And here I use n. N is just a number. And that would make this a limited number of terms. Finite sequence ends up being a limited number of terms. Where each entry is a term. Okay. So another example of this would be something like, I could say, to give you one where there's no n in it, 1, 2, 3, ... 5, and I just chose 5. I would never do, you never do ... for just one number like I am here, but that would be 1, 2, 3, 4, and 5. Where the dots just filled in the pattern between 3 and 5. The pattern was add 1 each time. That's a finite sequence. If we have an infinite sequence, is like a finite sequence, except it has an infinite number of terms. Has an unlimited number of terms or quantity of terms. And here we might see something like this. Just to give you an example, n plus 1, but we keep going up and we don't stop. We go all the way up to infinity. And sometimes, usually we don't like writing it like this because this can be really long. The ellipse is short in it, but still it can be long. Oftentimes we will write it in a function form. So when it's written in function form, as we'll do a lot today, so I'm not going to give you an example. at this moment, but we will in a second. Written in function form. We don't use f of x. Remember, functions have something like that. X indicates a variable, and these aren't variables. Which these are not. So we use f of n. Which reminds us that n are numbers, not variables. And they're usually natural numbers. All right. All right. Pause that if you need it up longer. The nth term is called a sub n. It's written like that, and it's pronounced a sub n. So just give you a quick example. If I had something like 1, 3, 5, 7, 9, that would be a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. To represent the first term, the second term, the third term, the fourth term, and the fifth term. So the n isn't necessarily the number that it is in the sequence. It's that number. It's that many items n. And this seems to follow some sort of pattern when we can write the pattern in a simpler form. So repetitive or patterns follow some sort of repetitive sequence. They don't have to. It could be all over the place. And we usually list it as an equation. Patterns follow some sort of repetitive sequence, usually, but not necessarily. And when they do, we write these as equations. Okay. And like an example of a sequence of numbers that don't follow a pattern, the lotto drawing, they draw 6 numbers, they're in order. While it doesn't matter to the people playing lotto if you get them in order, if you get the right numbers, you get the right numbers. They are drawn in order and they're not in some pattern, they're random, okay? But oftentimes they're repetitive. And so here's an example. Let's have a sub n equal 5n minus 2. And we will, let's find the first 5 terms. Okay. So how are we going to do that? Well, the first term is going to be a sub 1. And when here, notice that n and 1 have the same spot, we're going to replace n with 1. So I've got 5 times 1 minus 2 is 3. So a sub 1 equals 3. If I do the second term, a sub 2 is 5 times 2 minus 2. 5 times 2 is 10, minus 2 is 8. And we can go through each of these. And why don't you pause this and fill this in and figure out what the next 3 terms are. I'll assume you did. I'll go through and do them right now. A sub 3, 5 times 3 is 15, minus 2 is 13. 5 times 4 is 20, minus 2 is 18. And 5 times 5 is 25, minus 2 is 23. A sub 5 is 23. You may notice to get from a sub 1 to a sub 2, I had to add 5. To get from a sub 2 to a sub 3, I had to add 5. A sub 3 to a sub 4, I had to add 5. A sub 4 to a sub 5, I had to add 5. And that's not coincidence what we're adding. You know, repeated addition is multiplication, and that comes in right there. F5. Repeated addition is multiplication. You said that before. Let's write it down again. Fresh in memory. Now notice the first term here didn't start with 1. N equal a sub or n equals 1 did not give us the first term of 1. So I could rewrite this another way. I'm going to show you right now. Pause this if you need it up longer. We're going to use this formula again right now, though, okay? So I'll rewrite that down right now real quick. A sub n equals 5n minus 2. And some patterns or sequences can be written using a recursive definition. Okay, and a recursive means the latter terms are written in relation to previous terms. To a previous term. And for that to work, you have to have some starting term. You can't, to have the beginning point, you need a starting point. So an example of that, our first term here, a sub 1 was 3. And we just showed that to get from one number to the next, we added 1. We could say a sub n equals a sub n minus 1 plus 5, where n is greater than or equal to 2. And does that work? This way you don't need to write out the whole pattern to figure out what they are. That's the point of this. You don't need the whole pattern or whole list to find out a particular number. For a particular term. A sub 5. Well, not really. You kind of need previous terms of some sort. Let me cross that out. We'll get to something where you don't need the previous term, but I told you this was early. I'm making this early. So let's look at an example. We saw earlier that a sub 5 equals 23. Following this pattern here, though, a sub 5 would be this, which makes n equal 5. If n equals 5, n minus 1 is 4, a sub 4 plus 5. And a sub 4 we saw was 18. So 18 plus 5 does equal 23. Let me give you another one to tinker around with. I want you to pause the video after I start it, and I want you to write the first 5 terms. First 5 terms of a sub n equals -1 to the n plus 1 power times n squared. All right. I'll assume you paused it. Let's work it out. We'll do a sub 1. That is -1 to the 1 plus 1 power times 1 squared. This gives me -1 gets squared times 1 squared. -1 squared is just 1, and 1 times 1 is 1. So a sub 1 is 1. A sub 2, -1 to the 2 plus 1 times 2 squared is -1 to the 3rd power times 2 squared. And when we're just squaring or raising -1 to a power, it's just giving us a number of negative signs. So even number of negative signs is positive. An odd number on the exponent gives us a negative result. Oops, I wrote 4 because that's what 2 squared is. -1 cubed is -1, and 2 squared is 4. So that gives us a sub 2 equals -4. A sub 3 is -1 to the 3 plus 1 power times 3 squared, which is -1 to the 4th power times 3 squared. Is 1 times 9. A sub 3 equals 9. Okay. A sub 4, -1 to the 4 plus 1 power times 4 squared. This gives us -1 to the 5th power times 4 squared. -1 to the 5th power is an odd power. This is going to be -1 times 4 squared is 16. And that's going to give us -16. And you'll see we're just having the sign changes, positive, negative, and we're just doing the next squared number. So we're doing n squared. N squared would be 25, and the next sign would be positive. So in this sequence, the signs alternated, right? don't know why my hands got doing that already. That's bad. When we have a sequence that alternates, we call it an alternating sequence. I should say alternating. I got my L and my T too close. So it goes back and forth, positive, negative, positive, negative, positive, negative. This one started with a positive number. It doesn't have to. It could have started with a negative number. All right. They're not always pretty. Let's just do the first 4 terms of this sequence. We're going to do a sub n equals 3n plus 2 over n squared plus 3. I encourage you to write it down and write them out. This sequence is going to be an infinite sequence, but we're just going to do the first 4 terms of it. So if you do that, the first term gives you 5/4. Then you're going to have 8/7, 11/12, 14/9, and it keeps going. Okay. If I write that as those as decimals, I've got 1.25, 1.1428, 0.9167, 0.7368. And just to fast forward this for you a little bit, I'm going to show you what some later terms are. In this one, a sub 10 is 0.3107. A sub 1 or a sub 50 is 0.0607. And a sub 100 is 0.0302. None of them are negative. The top can never be negative. We're just sticking in positive numbers and we're adding a positive number to 2. The top's positive. We square a number, no matter what the starting number was, it's never negative after you square it. Adding 3 to it's going to make it always a positive number. So every term is positive. It's not alternating. Every term is positive. So there's no negatives. That's important. And if you notice, and each term is less than the term before it. So if it keeps going down, but can never go negative, as n goes up, as n gets larger, each term gets smaller, but never negative. Never results in a negative. Which means a sub n is approaching 0. As n goes to infinity. Okay? Or as n goes to infinity, a sub n goes to 0. And when this happens, for large enough n, Notice right away the big difference. Notice each thing, there's a big jump going down. 1.25 to 1.14, that's a good chunk. For large enough n, if a sub n closes in on a real number, it doesn't have to be 0. Just as long as it's approaching some real number, they say, or we say, that the sequence a sub n converges to that number. Which makes a sub n is a convergent sequence. And the sequence before that, what did we have? We had a sequence that alternated but got bigger. Let's look at that one. That's a convergent sequence when it approaches some real number. The previous sequence we did, though, recall we had 1, -4, 9, -16, 25. This sequence is not closing in on a real number. That pin's dying. Let's throw it away. In on a real number. This sequence diverges. Or is a divergent sequence. So as you can imagine, when the movies came out that had those names, I got a big kick out of it because they had nothing to do with mathematics, but those terms are very much used mathematically. You will see the words sequence and or convergence and divergence a lot when you get to calculus. You may have heard of the most famous sequence. I'm betting you have. You may not know what the sequence is, but you have heard the name. You might know the sequence, though. The most famous sequence is the Fibonacci sequence. And this sequence leads to something called the golden ratio. When you compare consecutive terms, I'm not going into the golden ratio. That's not what this class is on. It's not a history class. If you were interested about golden ratio, it's an interesting topic. I would look up Fibonacci sequence and golden ratio. In this sequence, the first term is 1. The second term is 1. And a sub n equals a sub n minus 2 plus a sub n minus 1 for n greater than or equal to 3. This is why we use that. This is an example of a recursive formula. A sub n depends on 2 previous terms. And when you look at it, 1, 1, and you're just adding up the 2 terms before it. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. Then we got what, 21. 13 and 21 is 34. 21, 34 is 55, and it keeps going. It's the sum of the previous two terms. So that's what sequences are. And we are going to use we're going to have let's talk about series now. I said this chapter was on sequences and series. Let's talk about series. If we add up the terms in the sequence, we have a series. I'm going to use adding is sum, so we have a symbol for that. The summation notation symbol, I think I've used it before. It's like a funky capital E. This is the Greek capital letter sigma. And when you see it in math, when you see it, it means add shit up. Yeah, you didn't think I was going to write it, did you? I did. You're adults. So let me give you an example. Oh, we don't use A sub n anymore. We use S sub n. To indicate the sum of the first n terms. Okay. All right. Give you another good one. Let's give you an example. So, example. So we're going to have the summation. This is how we write it. We write the starting number below it, and we indicate what letter we're using. It's not always n. So I'm going to say I equals 1 to 3, which means we're going to do I equals 1, 2, and 3 of A sub I. And that means this one is going to be A sub 1 plus A sub 2 plus A sub 3. This would end up being S sub 3. Okay? And so if we have something like it going to the nth one, usually we don't put n here because n is our resulting number. If I equals 1 to n of A sub I, we've got A sub 1 plus A sub 2 plus A sub 3 plus dot 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 plus A sub n. That's S sub n. So this comes in two forms. If n is a real number, then S sub n is a finite series. Just like we have there. I equals 1 to n of A sub I. if n keeps going forever, if n is infinite, let me say that's a finite series. For an infinite series, that's the sum of an infinite sequence. And we write that a couple ways. We could write I equals 1 to infinity of a sub I. And another way you'll see this is you'll see this. I equals 1 to n of a sub I. LIM means limit. So this which means keep going until you get to the number. Keep going until the letter hits the number. Or reaches that number, I should say. That's one use of it. And you'll also see in calculus, limit also means as we approach that number. And I keep doing this little I thing. So I want to talk about that again for a second. This I right here, this is called the index of summation. It's just a placeholder, really. Limit very much is a calculus idea. So you'll see this in calculus. But I'm warming you up. You're getting there. All right. Let's take a look at some examples. I just gave you a short example, but we haven't actually used any numbers. Let's use some real examples. So let's do the summation. It doesn't have to be I. I'm going to use j now. J equals 1 to 5 of j squared plus j plus 1. Okay, so basically my a sub j is j squared plus j plus 1. Which means we need to do the a sub 1 term. So what we're really doing is the sum from j equals 1 to 5 of a sub j, which means we need a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And you don't need to write that part out. You can jump straight to just calculating what the terms are. So what's a sub 1? A sub 1 is j equals 1 at that point. 1 squared plus 1 is 3. A sub 2, 2 squared plus 2 plus 1. 2 squared is 4 plus 2 is 6 plus 1 is 7. A sub 3 is 3 squared plus 3 plus 1. 3 squared is 9 plus 3 is 12 plus 1 is 13. And so if you do this out for the first 5 terms, we've got 3, 7, 13. The next one should be 21, and a sub 5 is 31. That's my sequence. So the series and I didn't say I didn't say the series was or sequence was limited. Let's say a sub j is an infinite sequence. Okay, the series is we need s sub 1. S sub 1 is just a sub 1, which is 3. S sub 2 is a sub 1 plus a sub 2 is 3 plus 7, which is 10. S sub 3 is a sub 1 plus a sub 2 plus a sub 3. And I'm going to show you a little quick shortcut. A sub 1 plus a sub 2 was just S sub 2. This is S sub 2 plus a sub 3. So I don't need to keep adding up the previous ones. Just use the previous sum and add the next number. 10 plus 13, S sub 3 is 13, or 23. S sub 4 would be S sub 3 plus a sub 4, like I just said right here, the shortcut. So a sub 1, and what we got here, S sub 3 was 23, a sub 4 is 21, so S sub 4 is 44. And S sub 5 is S sub 4 plus a sub 5. 44 plus 31 is 75. Because a sub j is an infinite sequence, these sums are called partial sums. Because we haven't added up the whole sequence. We've only added up part of the sequence. Okay? These sums are called partial sums. If it was a finite sequence, of 5 terms, S of 5 would be the sum, not partial sum. Because it's the last one. S of 4 would still be a partial sum. We haven't added up the whole sequence. And I want you to notice this. We started off with one sequence. And if I look at these sums, the series is actually basically a new sequence, isn't it? Let me write that in words. So notice the S sub n values make up a new sequence. This is different from the first sequence. minus the S of n values. So I can write the partial sums as a new sequence. S of 1, S of 2, S of 3, S of n plus 1, keep going up to infinity. There we go. And what we had in the last example, we had 3, 10, 23, 44, 75, and it kept going. So just like we talked about sequences being convergent or divergent, let's talk about series being divergent or convergent. So a series, we only look at if it's a finite series, always convergence. Well, I can't, if it goes, well, yeah, it has to add up to a specific number. Finite series converges, assuming every term in the sequence was a real number. Was not infinity in the sequence. And we're never really going to have a sequence that has infinity and it just gets kind of boring. So an infinite series let's talk about it going two ways. It's divergent if its sequence of partial sums does not approach a real number. For example, this one, we keep adding a larger and larger number to it. This sequence up above, this last example, was not a, it was a divergent series. An infinite series is convergent, of course, if it does the opposite. If the sequence of partial sums does approach a real number. Converges on a real number. So if an infinite series converges, what does that mean for a sub n when n is really large? I actually want you to pause this video and think about that. Think about what has got to happen for a sub n for a series, the sum of numbers, to converge when we just keep adding new terms to it. What has to happen if they add up to or approach some real number? Okay, think about that. Pause the video and think about it. What this is really saying is if it converges, then the terms in a row have got to be pretty close to each other, right? S sub n has got to be approximately equal to S sub n plus 1. They got to be really close. Okay? But S sub n plus 1 recall is just S sub n plus A sub n plus 1. So I've got S sub n plus 1 is approximately equal to S sub n. I'm sorry, S sub n is approximately equal to S sub n plus A sub n plus 1. Let's do a little bit of algebra. Let's subtract S sub n from both sides. And we're going to get 0 is approximately equal to A sub n plus 1. Pause that if you need it up longer. So what that means, so if an infinite series converges, A sub n has to approach 0 as n approaches infinity. Okay? So let's give you some examples of some series that look convergent or that are really close to each other but converge or diverge. An example, a couple examples. Our first scenario, we're going to have S sub n is the summation of I equals 1 to n of 1 over n, or 1 over I. Say to infinity, I equals 1 to infinity of 1 over I. This is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And it keeps going. This actually does not converge to a real number. This is a divergent series. Even though the sequence converges to 0. Okay? This is deep. This is one of those weird ones. This is abnormal or unusual. But one that looks very, very similar if we have S sub n equals the summation of y equals 1 to infinity, negative 1 to the I plus 1 times 1 over I. This is 1, the first term's 1, then it's got the same terms, but they alternate signs now. This is a convergent series. It actually adds up to a real number. You'll explore this in calculus. This is a very popular one in calculus. And I don't want to spoil it for you, so just wait for it. So how will you see this in calculus? Let me just give you an example. You'll see stuff like this. Let's say we have some function f of x. And it's broken up into numbers that are delta x apart. That's read delta x. So remember, like f of x, we could do some graph. Like doing like this. That's f of x. We're doing x's right down here. Our x values are all delta x apart. So delta x is a width. And you'll look at doing summations of these. You'll do something like the summation of k equals 1 to n of f of x sub k delta x. And you'll have, that's f of x sub 1 times delta x plus f of x sub 2 times delta x. And it keeps going, f of x sub n times delta x. And when you get to calculus, delta x is going to go towards 0. We're going to try to make that width narrower and narrower and narrower. And what is each of these things? F of x sub 1, let's say this is x1 right here. F of x sub 1 is this thing right here. That's really a height. And delta x is the width. And if we're multiplying the two, f of x sub 1 times delta x, you're ending up with a rectangle. So this thing is actually calculating the area under a curve. Again, calculus. That's why I'm showing this to you, though. This is very important. Chapter 11 is very important to your future. You're going to see this a lot. All right? And where you'll see it in calculus, real quick. So as delta x goes to 0, we're going to have limit as n goes to infinity of the summation of k equals 1 to n f of x sub k delta x. You're going to see this, a big giant curly looking s that's kind of flattish, flat s, f of x dx. This is called an integral. And notice this is just, we were doing the area under the curve. It's just area under a curve. Okay? You're not, that's not in this class. You're not being tested on that. This is just where we're going with it, where you're going to go with it and why you need to learn this. Okay? So let's look at some cool properties of series. Maybe I should make a note for that. Not on your test, but shown to see the importance. So you understand the importance. Like, why are we adding up numbers in a sequence? Who gives a shit, right? Who gives a shit? Well, there's a reason why we give a shit. So cool properties of series. Let's say C equals a constant number. And we'll have A sub 1, A sub 2, A sub n, and B sub 1, B sub 2, dot, 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 B sub n are sequences. That's the information we need for the following cool properties. If we add up I equals 1 to n of C, just the constant number C, this is C plus C plus C plus C, where there's I different C's, or I number of C's. Or sorry, n. I equals 1 to n, n number of C's. This just gives us n times C. So the summation of a constant sequence it ends up being multiplication. Now the cool one. So if we take that same idea, we're going to do I equals 1 to n. We're going to do C times A sub I. I can actually pull the C out and just do I equals 1 to n of A sub I. And I keep saying it, I want to make sure you know, I is lowercase capital I, okay? I write it that way so it doesn't look like a 1. That's the why I give it a little tail. It's how it looks on typewriters too. It doesn't look like a 1. You can't mistake it for a 1 with a curl. I recommend you do it too. You'll like it. Or it'll save you headaches in the future to get used to it now. Another cool one. We could add up 2 different sequences. And that's the same thing as adding up the 2 different sequences, or finding the sum of 2 sequences and adding them together. It's almost like the summation distributes. That's not really what's going on. So some cool summations. Some common summations. And do I equals 1 to n of I. This is 1 plus 2 plus 3 plus dot 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 plus n. Let's just say n minus 2 plus n minus 1 plus n. Okay. And this might be easier to see by giving an example. Let's say n equals 50. I'm going to show you with the shortcut. There's a shortcut solution to this. This is our summation is I equals 1 to 50 of I, 1 plus 2 plus 3 plus 4 plus ... plus 48 plus 49 plus 50. Now, I could add all these up, but notice if I add up 3 and 48, 3 plus 48 equals 51. 2 plus 49 equals 51. 1 plus 50 equals 51. So if I keep adding up the outer terms and go inwards, all these sums add to 51. And how many pairs of these would I do? The inner pair would be 25 plus 26. 25 plus 26 is 51. That's the inner pair. And we're going 1, 2, 3, 4 up to 25. There's 25 pairs. Which notice 25 is 50 over 2. Which is n over 2. Because n was 50, right? Each of these is 51. Each of these is n plus 1. So if I have, what I'm doing is I'm adding up 25 sets of 51, repeatedly adding the same number as multiplication. This would be 25 times 51. Okay. And whatever that value equals is not the important thing that we're going with. This ends up being n over 2 times n plus 1. That's the shortcut for this series. It's n times n plus 1 over 2. And here I just put the n plus 1 on top. This is just as valid. This is actually a little bit easier to see where it's coming from. Same thing up there. So rewind that if that didn't make sense. We're doing each, adding up the outer numbers, then the next set of inner numbers, next set of inner numbers. They all add to the same number. How many times we're doing it? We're doing it half the total number of times. And when you keep adding up the same number, you're really multiplying. Just like we showed here. What we're doing, what this shortens down into is I equals 1 to 25 of 51. That's really what this shortcut ends up being. Some other fun ones that fall in this problem, I don't know how fun they are. That top one's the most common one you'll see. Less common, but ones I'm sure the homework will throw at you. I equals 1 to n of I squared. Rather than trying to derive it for you, which would be a pain in the ass. N times n plus 1 times 2n plus 1 divided by 6. And you see I equals 1 to n of I cubed. This is n squared times n plus 1 squared divided by 4. These are less common and more of a pain to derive. But those are the examples, so let's look at a few examples. We're going to use these properties to figure out the following. Let's do the summation of I equals 1 to 3. We'll keep it small. Small summation. I cubed plus 2i minus 8. remember when we had a bunch of things added together, we could break this up. This is the same thing as the summation of I equals 1 to 3 of I cubed plus the summation of 2I from I equals 1 to 3. But remember, I can put the 2 on the outside. That was one of the cool properties. Put the 2 on the outside. And then minus the summation of I equals 1 to 3 of 8. And we had formulas for each of these. So n here is 3. So our I cubed one, we had I cubed was n squared, so 3 squared over 3 plus 1 squared over 4. That's the I cubed one. Plus 2 times the I one. I was n times n plus 1 over 2. And when we added up the constant, it was just n times the constant. What does this end up giving us? So we've got, this is n squared times 4 squared over 4. One of the 4's will cancel on top and bottom. And this is, look here, the 2's cancel. I just got 3 times 4 minus 3 times 8 is 24. So I've got, oops, I don't need that parentheses right there. 9 squared is, not 9 squared, just 9. 3 squared is 9. So 9 times 4 is 36. Plus 3 times 4 is 12. Minus 24 is 24. Okay. That's an example of applying these. That was 11.1. They're going to give you a bunch of stuff there. Let's take a look at 11.2. 11.2 is on arithmetic sequences and series. So an arithmetic sequence is when the difference between consecutive terms is constant. And we're going to call that constant difference D. We're going to go with lowercase d. D for difference. The common difference between terms. Which means rather than writing it out, I can just say that a sub n plus 1 is a sub n plus that common difference d. We saw one not too long ago. We had 3, 8, 13, 18, 23. So a sub n plus 1 equaled a sub n plus 5. Sometimes we don't know the d, but we can figure it out. How did I figure this out? 8 minus 3 is 5. Well, I can do 23 minus 18 is 5. Just take the common difference between two consecutive terms. So subtract one term, subtract the previous term from your current term. So quick example for you to figure out, what is d if we have the sequence 20, 13, 6, -1, -8. Try to figure that out real quick. Doesn't matter which two I use. D equals 13 minus 20 is -7. D equals -8 minus -1 is -8 plus 1, which is -7. D equals -7 for that sequence. Okay? And that's the sequence. Let's look at a series that has this. Well, not quite. Let's not do the series yet. Let's look at a large term. Let's go up pretty high. So we've got a sub 1 is just a sub 1. A sub 2 is a sub 1 plus d. I'm going to say 1d. A sub 3 is a sub 1 plus a sub 2 plus a sub 3, which is a sub 2 plus d. I don't want to put that in there. We're using a sub n plus 1 equals a sub n plus d. I want to throw it off. But a sub 2 is there. This is a sub 1 plus d plus d. So I've got a sub 1 plus 2d. A sub 4 is a sub 3 plus d. But a sub 3 we just had over here. A sub 1 plus 2d plus d, which is a sub 1 plus 3d. A sub 5, a sub 4 plus d. We just had a sub 4. A sub 4 is a sub 1 plus 3d plus d. And so this is a sub 1 plus 4d. So n equals 1, n equals 2. Let's just take a look at this. I had a sub 1 equals a sub 1, a sub 2 equals a sub 1 plus d, or 1d. A sub 3 equals a sub 1 plus 2d. A sub 4 equals a sub 1 plus 3d. A sub 5 equals a sub 1 plus 4d. Just taking this information I had here and making a little table. And if I say I'm adding nothing to it, I could say plus 0d. What if I don't want to use n's? Or what if I don't want to do these individual numbers? How does this number here relate to the n's? This number here is n minus 1 for each of these. 4 is 5 minus 1, 3 is 4 minus 1, 2 is 3 minus 1. I could write this entire thing, the generic formula for an arithmetic sequence, is a sub n equals the first term plus, I'm not going to use the numbers now, I'm going to use the n minus 1 times the common difference. Okay, an arithmetic series, of course, is similar. Arithmetic series is the sum of an arithmetic sequence. Recall we had S sub n for I equals 1 to n of I equaled n times n plus 1 over 2. But how does this relate to our arithmetic sequence? N, this was 1 plus 2 plus 3 plus dot 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 plus n, remember? So this is a sub 1, and that's a sub n. Which really means S sub n here, I equals 1 to n. N is just a sub n. I've got a sub n over 2. Let's not put in a sub n. Let's just leave it right there. Let's just leave it as n. Let's work on these two. Let's replace those. That's a sub n plus 1, or a sub n plus a sub 1. Okay. So I've got n over 2, and I know a sub n following this formula right here. We're going to use this down there. A sub 1 plus n minus 1 d. That's my a sub n. And we're adding to that a sub 1. So if I wanted to write the arithmetic sequence of these, S sub 1 or S sub n is n over 2. And I've got two a sub 1s right there now, right? Plus n minus 1 times d. I don't know why you do it. I think it's easier just to do the other way, but there's an example of it working right there. Why does this help? We can find the sum if we know the first term. Well, first two terms. I really need the difference, right? Let's do some examples of let's do some examples with this arithmetic sequence. So I've got a sub n equals a sub 1 plus n minus 1 times d. Look, I have enough problems in my notes right now that I want. Let's grab some examples, take a look at them. That's some problems I want to use. Let's look at some examples. Let's find the first few terms. If a sub 1 equals, let's go with -8, and d equals, oh, let's use a negative number. Let's go with -3. Well, we've got the first one pretty easy. A sub 1 equals -8, right? What's a sub 2? A sub 2 equals a sub 1, which is -8, plus 2 minus 1, which is n, times d, which is -3. So I've got -8, 2 minus 1 is 1, -8 plus -3 is -11. A sub 3 is -8 plus n minus 1, n here is 3, times our difference d. 3 minus 1 is 2, so 2 times -3. This is -14. And it gets kind of easy. We're just subtracting 3 each time, right? So that part's fairly straightforward. Where will make it a little more tricky for you, you'll see problems like this. This was simple. Let's do trickier. Find a sub 13 and a sub n for the sequence -3, 1, 5, 9, ... Now, I kind of threw it into a funny order. This might be easier to figure out a sub n first, right? But for a sub n, we need a sub 1 and we need d. So those are easy though. What's a sub 1? A sub 1 here is just the first number. D is the difference between any two consecutive numbers. I'm going to choose some easy ones, 1 and 5. 5 minus 1 is 4. So a sub n equals a sub 1, which is -3, plus n minus 1 times d. I'll put the d in front, 4. That's a sub n. That means a sub 13 is -3. That's our a sub 1. Plus 4 times n is 13. 13 minus 1 is -3 plus 4 times 12. -3 plus 48 is 45. Do I want to leave a sub n like that? No, let's not. Let's clean up a sub n. It's ugly like that, right? A sub n is -3 plus, let's distribute the 4, 4n minus 4. And if I gather like terms, a sub n equals 4n minus 7. And if I had done that first, notice how easy a sub 13 is. A sub 13 is 4 times 13 minus 7. 52 minus 7 is 45. It's even easier. Might have been easier to clean up a sub n. I just clean it up by distributing the difference. What else will they give you? Oh, they may not give you the first ones. Let's give you another example. Let's find a sub n and a sub 18. If, let's go with a sub 4 equals 21 and a sub 5 equals 27. Okay. Well, we can find the difference, right? We don't know the first term yet, but we can find the difference. The difference is a sub 5 minus a sub 4, which is 6, right? 20. I wrote a sub, what the hell did I write here? I wrote a sub 27 or a sub 7. I want to write 27 there. 27 minus 21 is 6. My bad. So D equals 6. How can I find a sub 1? So that part's easy. Let's find a sub 1 by using what you have. So let's just use, I'll use the smaller one, a sub 4. A sub 4 equals 21. But a sub 4 should equal a sub 1 plus 4 minus 1 times D. And if we plug in what we know, a sub 4 is 21, plus 4 minus 1 is 3, times D is 6. 21 equals a sub 1 plus 18, so a sub 1 equals 3. Which means a sub n is 3 plus n minus 1 times D, and I'll put the D in front. And just like I did last time, I'm going to clean that up. I'm going to distribute. This is 3 plus 6n minus 6. So a sub n equals 6n minus 3. And we wanted a sub 18 equals, we're going to do 6 times 18 minus 3. 6 times 18, we've got 60, and 48 is 108, minus 3 is 105. Make it a little bit trickier. They may not be in a row. I put these two in a row. Let's kick it up a notch. Find a sub 1 here. That's all we're going to do. Find a sub 1. And what we're going to have is a sub 8 equals negative 16, and a sub 16 equals negative 40. So we know to go from a sub 8 to a sub 16, a sub 8 has to equal, or a sub 16 has to equal a sub 8 plus 16 minus the number of steps we've taken. Of the difference. And where did I get these two values? 16 is right there. 8 is right there. That's not something I think I pointed out earlier. When we had a sub n equaled a sub 1 plus n minus 1 times d. It's those numbers right there. Okay. And what do we have here? A sub 16 is negative 40. A sub 8 is negative 16. Plus 16 minus 8 is 8. And we don't know the difference yet, d. And so we can solve for d. I can add 16 to both sides. And I get negative 24 equals 8d. Divide by 8, and I get d equals negative 3. Now I've got d, I can plug it in, a sub n. A sub 1 plus 3 times n minus 1. Where I'm putting the d in front, now that I know what it is. And now I'll pick the smaller one. Let's do a sub 8. A sub 8 equals a sub 1 plus 3 times 8 is my n, 8 minus 1. And a sub 8 was negative 16. So what do I got here? I've got a sub 1 plus 8 minus 1 is 7. So 3 times 7 is 21 equals negative 16. D is not positive 3, it's negative 3. Which means that's minus 27, or minus 21. If I add 21 to both sides, I get a sub 1 equals 5. So that's the kind of stuff they'll have you do. Okay. Let's take a look at, that's 11.2. 11.2 is not too bad. 11.3 is not too bad either. 11.3 is on something called the geometric sequence. And where arithmetic was addition between terms, the geometric is similar, but it's not addition, it's multiplication. And we're going to call that multiplier. We want the multiplier to be constant. With a constant multiplier, we're going to call R. R, maybe. And another name for this R is also called the common ratio. Why is it called that? Well, if it means multiplication between consecutive terms, this means a sub n plus 1 is really a sub n times that multiplier r. And if you divide both sides by a sub n, you're going to see r equals a sub n plus 1 over a sub n. And that's a ratio. And this thing is going to be common between each two consecutive terms. Okay. I want to go straight. And so that's the geometric sequence. So let's look at a quick example. Let's say d equals 1/2, and a sub 1 equals 1. My sequence would be 1, and then 1/2 times 1 would be 1/2. 1/2 times the previous term is 1/4. And it goes on like this, where this is just the first term, and then I've got 1/2 times the previous term, and we're going to just do 1/2 times the previous term on each of these. Would be there. So that's an example of a geometric sequence. The fun part is in the geometric series. Actually, let's look at an example of finding ones. So let's give you an example. Find a sub 1 and r if a sub 3 equals 20 and a sub 6 equals 160. Actually, let's come back to that. Let's make a shortcut formula for doing a sub 1. Let's find a sub n plus 1 in terms, let's find a sub n in terms of a sub 1. Okay. I'll do that real quick. So a sub 1 is just a sub 1. A sub 2 is a sub 1 times r. A sub 3 is a sub 2 times r. But we just saw that a sub 2 is a sub 1 times r. That's my a sub 2 times r. So I've got a sub 1 times r squared. A sub 4 is a sub 3 times r. But a sub 3 was a sub 1 r squared times r. This is a sub 1 r to the third. And if you see the pattern here, I could write in r to the 0 power here and r to the first power there. a sub n equals a sub 1 times r to the n minus 1. Okay? Now let's go back to that problem. Back to the problem. A sub 3 equals 20. A sub 6 equals 160. Find a sub 1 and r. So again, notice this n here is that n there, and this one here is that one there. So I could write a sub 6 in terms of a sub 3. A sub 6 equals a sub 3 times r to the n minus, which n is 6, and this is 3. A sub 3 times r cubed. Okay? And if that's the case, we can plug in what we have. So I'll put it all together. A sub 6 equals a sub 3 r cubed. And I've got a sub 6 is 160. A sub 3 is 20. And we can solve for r. Divide both sides by 20. We get r cubed equals 8. And we take the cube root of both sides. We get r equals 2. Now we'll find the other one. Find a sub 1. I'm going to use a sub 3 because it's a small number. We got to go into our formula. A sub 3 equals a sub 1 times r to the n minus 1, which is 3 minus 1. So a sub 3 was 20 equals a sub 1 times r, which is 2, to the 3 minus 1 is 2. So 20 equals a sub 1 times 2 squared is 4, and get a sub 1 equals 5. That's a challenging example. They might have given you a sequence to start off with. Let's say the sequence was, let's do 4, 12, 36, 108. Find r. And let's end a sub 6. All right, so what's r? We could take any two consecutive terms and divide it. R is a sub n plus 1 over a sub n. I'll just use the first two terms. 12 over 4, that's the easiest one to do, is 3. So r equals 3, which means a sub n equals a sub 1 times 3 to the n minus 1. Okay? And if we want a sub 6, a sub 1 times 3 to the n minus 1 is 6 minus 1, which is a sub 1 times 3 to the 5th power. What is 3 to the 5th power? What's a sub 1? A sub 1 is 4. Times 3 to the 5th power. Calculator. It would disappear. There it is. Is 4 times 243 is 972. And that was a sub 6. All right. So those are examples of geometric sequences. If we look at the geometric series, again, this is a sum of a geometric sequence. And it comes in the form S sub 1 equals a sub 1 over 1 minus r to the n over 1 minus r. And hopefully, well, not hopefully, but probably your first thought is WTF, how in the hell did we get that? I'm actually going to show you. Not too bad once you see it. So S sub n, we know what S sub n is. S sub n is a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n. And in the geometric sequence, this is a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r to the n minus 1. And what is r times that? If I look at r times s sub n, I'm going to line them up underneath consecutive r's. So r times a sub 1 would be a sub 1 times r. And this one right here, if I multiply this one by r, I'm going to get that one. And if I multiply this one here by r, I'm going to get a sub 1 times n minus 1 times r is adding another 1 to the exponent is just r. So that would have been plus a sub 1 r cubed plus dot dot dot. And now what I'm going to do is I'm going to subtract that second one from the top one. So s sub n minus r times s sub n equals, if I just subtract this, this goes away, this goes away. The term before this, I'm going to write this over here. Ooh, shit. A sub 1 r to the n. The term before it would be n minus 1. There we go. Multiplying that term by r, I get a to the a sub 1 times r to the n. And the term before that would have been a sub 1 times r to the n minus 1. When I subtract them, all of these cancel out, and I'm just left with a sub 1 plus a sub 1 r to the n. Cancels in subtraction. All right, so here I can, but this, since I'm subtracting it, this one's a negative. That's a negative. Okay. So what do I have here? I can factor out the s sub n. I've got s sub n times 1 minus r equals, here I can factor out the a sub 1. I've got a sub 1 times 1 minus r to the n. And now they divide by the 1 minus r. Okay. So how would we use this? Let's say you win the grand prize in a raffle. And you get two choices. Option A, $300,000 in one lump sum. Or B, for 30 days, double your payment from the previous day. Where day one equals a penny. A single penny. Which of these do you choose? Well, we know what A is. Let's figure out how much money will we get if we just were patient and did B? How much would B equal? If we are patient. Well, double means 2. Our multiplier is 2. Which means a sub n equals 2 times a sub n minus 1. Or a sub n equals what? What do we got here? A sub 1 times r to the n minus 1. Remember? And rather than figuring out what it looks pretty bad. We got, if you look at starting the sequence, we've got $0.01, then we got $0.02, then we've got $0.04, then we got 0.08, then 0.16, then 0.32. What's 1 week? 1, 2, 3, 4, 5, 6, 7. Week 7, your 7th payment is 64 cents. This is not looking good, right? Doesn't look good after 1 week. What's A sub 30 then? A sub 30 is A sub 1, which is $0.01, times R, which is 2 to the 30 minus 1, or 0.01 times 2 to the 29th power. 2 raised to the 29th power is that, times 0.01. That's how many pennies we have right there. $536,870,912. That's how many pennies on day 30. Multiply that by 0.01, just shifts the decimal left twice. 5 million bucks on day 30. Is A sub 30. That's not what I asked you though. Well, obviously you're going to choose B, right? Because the 30th day is way more than 300,000. What's your total payment though? What's the total payment with option B? Let's do that on another page. Recall S sub n equals A sub 1 times 1 minus r to the n over 1 minus r. This is 0.01. 1 minus 2 to the 30th power over 1 minus 2. One minus 2 is -1. I can just put that out in front. -1 on bottom is the same as -1 on top. -1 times 0.01 times 1 minus 2 to the 30th. The -1 is throwing me off a little bit, but notice when we do this, this is going to be negative and it's going to be end up going to be positive. So what's 2 to the 30th power? And I'll do minus 1, or 1 minus that. This would be S sub 30 now, not S sub n. So I've got -1 times 0.01 times 0.073741823 in the billion range. Now I multiply that by -0.01. S sub 30 is $10,737,418.23. Interesting, right? When does our sum equal? When does our sum exceed the 300,000 of option A? How long would it take till we get to the 300,000? Or when is S sub n greater than or equal to 300,000. Let's see if we can figure that out. This is not in my notes, but I like this problem. This looks good. This is the smart thing, right? How long does it take? So S sub n, though, S sub n is a sub 1 times 1 minus r to the n over 1 minus r. And that's 0.01 times 1 minus r to the n, or 2 to the n, over 1 minus 2. And the 1 minus 2 is negative 1. This is negative 0.01 times 1 minus 2 to the n. Can we figure this out? Do we have the skills? Do we have the power? When is that greater than or equal to 300,000? Let's divide both sides by negative 1.01. So 1 minus 2 to the n is greater than or equal to, nope. Dividing by a negative switches the sign. Less than or equal to, dividing by 0.01, I think is the same thing as multiplying by 100. Yeah. Is less than or equal to 30 million. I don't need that parentheses anymore. Subtract the 1. So negative 2 to the n is less than or equal to 29,999,999. Let's change the sign. So 2 to the n is greater than or equal to negative 29,999,999. Something's off. Two to the n would always be greater than that. What did I do wrong here? That's S sub n. That has to be greater than 300,000. Oh, I divided by negative 1.01. That would have made that negative. That's negative. That becomes positive. That's where I went wrong. And this becomes, if we take log base 2 of both sides, remember that's how we get the n out of the exponent. And log base 2 there. I get n equals log base 2 of 29,999,999. Which is log base 10 of 29,999,999 over log of 2. Divided by log of 2. N is 24.838 days. So 25th day. That's when we'd exceed it. Oh, the logarithm stuff coming back. That's neat. All right, let me tell you one more thing about geometric series and we'll wrap this up. I'll do 11.4 in a little while. I need a break though. Let's look at infinite geometric series. Or S sub infinity. Yeah, let's just do an example. Sequence. We're going to have is 4 4/5, 4 over 25, 4 over 125, which means our series is adding these up. 4 plus 4/5 plus 4 over 25 plus 4 over 125 plus dot dot dot. What's my A1? A1 is 4. What's R? Let's just do 2 consecutive terms. R equals, I'm going to use the later terms just to make it remind you of your fractions. 4 over 25 divided by 4 over 5. Clean that up. We're going to multiply top and bottom by the reciprocal of the bottom. The bottom goes to 1. Here the 4's cancel, and I'm left with 1, 5 over 25. The 4's cancel. 5 over 25 is just 1/5. So what's going on here? Let's just figure out, let's look at what the partial sums are. Partial sums. S sub 1 is 4. S sub 2 is 4.8, which is 4/5. S sub 3 is 4.96. S sub 4 is 4.992. I'm just keep adding these things up. I'm just giving you a few here. This is obviously calculator work. I'm not doing this in my head, and I've already pre-done this to expedite this. It keeps getting larger, but it doesn't go above 5. As n goes to infinity, S sub n goes to 5. And where is that stemming from here? S sub infinity equals 5. Which is our first term, times 1 minus 4/5. 1/5 to the n over 1 minus 1/5. That's a little fuzzy. Something's off here. Yeah, that's what's off. The n is on the inside. 1/5 to the n as n goes to infinity goes to 0 as n goes to infinity. So I've got 1 minus 0. This is just 4 on top. 1 over 1 minus 1/5. And how's that look here? This is a sub 1 over 1 minus r. Okay? So let's just finish up that idea. S sub infinity is a sub 1 over 1 minus r. We don't, obviously, r cannot equal 1. It breaks the bottom. And if r is a fraction, if it's between -1 and 1, this is the same thing as saying the absolute value of r is less than or equal to 1. Let's say less than. I can't have equals. Less than. If the absolute value of r is less than 1, this converges. Just like in our last problem, r was 1/5, the sum converged to 5. Outside of that, or the absolute value of r is greater than 1, which means r is less than -1 or r is greater than 1, it doesn't converge. It doesn't converge. The sum does not exist. And it's a divergent series. All right, that wraps up 11.3. I will do 11.4 in a little bit, and we'll take a little break. Peace.